Okay, so I'll just be doing a quick CDL design demo for the CDL Standalone Core. So as I explained earlier, this is where you have the core that can only run one single network and it's highly optimized. What we'll be using as a neural network is SqueezeNet, trained for person presence detection. So it only detects whether there's a person present in the image or not. Okay, so I've already quantized this network and we'll be going through the flow to actually get the configuration for the CDL core itself. So for CDL design, we start with a project file. So this is the project file for this network, and for the FPGA that we're targeting. As input, it takes the network itself as the CDL network in that format, as well as the coefficients, which is the weights and the biases. And then we point it towards a directory where the network will be exported to. From there we go to the configuration of the CDL core itself. So we're going to be using a shared memory layout. That is where you have a space for the weights and the biases, and then input and output spaces that's repeated. So you can ping pong between the like, let's say you're processing one network and then you're uploading the results of the previous run and downloading data towards the FPGA, so it has the data for the next iteration ready. And then it has a shared heap space, so it minimizes memory use by reusing this shared heap space for all the intermediate layer processing. So we are going towards the core configuration itself. We tell it the platform that we're targeting, which is the Smart Vision 2 M2S010, and we're telling it to reserve math blocks on the network such that there's only 12 math blocks left. We're setting the frequency to 140 MHz. And we only allow 3 AXI interfaces for the inputs and 1 for the output, and we tell the design space exploration to go for maximum performance. So this platform and reserved file points towards data files that's already set up for CDL design. We provide quite a few platform files for micro, semi, microchip FPGAs. So this is the platform file for the chip that we're targeting today. As you can see, it has 22 math blocks, and then we have a reservations file. Yeah, this one that reserves 10 of those math blocks such that we only have 12 left. Okay, so from here we only need to run the script. So I have So we are going to be using the CDL Design executable. We tell it to export the design, so it's actually going to write the results. And then we just point it towards the project file. Okay, there we go. It's already completed. As you can see, it went through around 20,000 designs to get to this optimal one. It's quite a low number compared to what we see for the bigger FPGAs that might go to like through 1 million designs or up to billions of designs. So we have a small report here already, but we'll be looking at the report from CDL. It's actually written to this folder that we pointed it towards earlier. There we go. Okay, so firstly it has a whole section for the memory map. So we have quite a few regions, one for the weights, the biases, the shared heap space, and then here's the first input and output space. And then if we go down, we'll get to performance reports. So CDL Designs tells us it's expecting this network to run at 1.94 frames per second. And the core itself is capable of processing 2.88 giga operations per second on this network specifically. Also exported is the memory.hex file. It's also in the memory.bin file, it's the same data. So this is just the raw data that you need to upload to the DDR. It's the weights and the biases. And then a very important file is this packed parameters file. So this packed parameters file is used to configure the CDL core itself. So you have the CDL core IP in Libro and this packed parameters file, and that programs the CDL IP to run this specific network in this configuration. So from here it's the standard FPGA design flow in Libro itself.